Very good morning to all. In this lecture, we are going to discuss the basic concept related to electric field. So the first topic which we are going to cover is the concept of electric charge. So what is electric charge? In order to understand the physical significance of electric charge, let us try to study the atomic structure of an atom. We know that an atom consists of three main components. First one is proton, second one is neutron, and third one is electron. And we know that proton carry positive charge, neutron carry no charge, and electron carry negative charge. And if you take any atom, it is said to be electrically neutral because the number of proton and the number of electron are always equal, so they cancelled out each other, and we can say that an atom is electrically neutral in nature. But due to some technique, if it is possible to create excess number of electron in an atom or to create deficiency of electron in an atom, then we can say that that particular atom will attain some net positive charge. It may be positive or it may be, say, negative. Suppose due to some method, if we are capable to create the deficiency of electron in an atom, then it will attain a net positive charge, and due to some mechanism, if we are capable to create excess number of electron in an atom, then it will attain a net negative charge. So this particular structure is known as ion, and in this way we can define the concept of what? Electric charge. Mathematically, electric charge are indicated by symbol capital Q, and the unit of electric charge is coulomb, indicated by symbol capital C. So Q indicates charge and the unit of charge is coulomb. Now the next point is the concept of electric potential. What is electric potential? Electric potential is defined as the ratio of energy per unit charge. So energy per unit charge is nothing but electric potential, and mathematically electric potential is indicated by symbol capital V, and it is given by energy per unit charge. Now if energy is represented in terms of joule and charge is represented in terms of coulomb, then the unit to represent electric potential is nothing but joule per coulomb. And majority of the cases, electric potential is normally measured in terms of volt after a very famous scientist, Alexandro Volta. So the unit of electric potential is volt, or it is joule per coulomb. So I can say that 1 volt is going to be equal to 1 joule per coulomb, which is very important. Now what is the physical significance of this? For example, if we are having 2 points, point A and point B, and suppose the potential difference between these 2 points is say 2 volt. So from this definition I can write 2 volt as 2 joule per coulomb. That means in order to move a charge from point A to B, 2 joule of energy is maintained on each charge. That is the significance of electric potential. So electric potential is nothing but how much amount of energy is maintained on each charge. So that energy is nothing but electric potential. Now let us try to discuss the concept of Coulomb law. And electric field intensity. So what is Coulomb law? According to Professor Coulomb, he experimentally found that suppose if we are having two charges, say Q1 and Q2, separated from each other by a finite distance indicated by symbol small d, then these two charges may experience a force of attraction or they may experience a force of repulsion. It depends upon the polarity of these two charges. Suppose if both the charges are of same polarity, they will experience a force of repulsion, and suppose if they are of different polarity, they will experience a force of attraction. Then in that case, according to Professor Coulomb, the magnitude of force of attraction, or you can say repulsion, between these two charges is proportional to the product of individual charges, and it is inversely proportional to the square of distance between them. And let us consider that for our discussion both the charges are of same polarity, that means both are positive. Then in that case both the charges will experiences a force of repulsion. That means the charge Q2 will try to move away with respect to charge Q1, and charge Q1 will try to move away with respect to charge Q2. So in that particular case, this force is given by Professor Coulomb. So F is proportional to Q1 Q2 divided by d square. Now this proportionality sign is replaced by a proportionality constant indicated by symbol K multiplied by Q1 into Q2 divided by d square, where the value of this K is experimentally found as 1 upon 4 pi epsilon naught, where epsilon naught indicate the permittivity of free space, and the value of this epsilon naught is around 8.85 into 10 to the power minus 12 farad per meter. So from this equation, let this equation number 1, it is very clear that the force of repulsion between these two charges is given by F equals to K Q1 Q2 divided by d square, where K is nothing but a proportionality constant which depends upon the permittivity of that particular medium. Now, in the last lecture we discussed the basic aspect related to vector domain. So the same mathematical equation we can write in vector analysis also, because it is a force, so it has magnitude as well as direction. So let us try to write equation 1 in vector analysis domain. So for that, let us consider that we are having a two-dimensional plane. Somewhere over here, this arrow indicate x-axis and this arrow indicate y-axis. And let us consider that at this particular point we are having charge Q1 which is at a distance of r1 bar with respect to origin O. In the same way, somewhere over here we are having another charge Q2 which is at a distance of vector r2 bar with respect to origin. And the distance between these two charges is indicated by another vector which is r12 bar. So from this particular figure it is very clear that small r1 bar indicate a position vector which indicate the position of charge Q1 with respect to origin. Similarly, small r2 bar indicate a position vector which indicate the position of charge Q2 with respect to origin, and capital R12 bar indicate a distance vector, or it will indicate the distance between charge Q1 and charge Q2. Let us consider this arrow indicate the direction of a unit vector along a line joining these two charges, which is indicated by symbol small r cap. So small r cap is a unit vector along a line joining these two charges. Now, as I told you that we have considered that both the charges are of same polarity plus plus, That means both the charges will experience a force of repulsion with respect to each other. So let us consider that our charge q1 is fixed and our charge 2 is movable in nature. Then in that case, this charge q2 will experience a force of repulsion with respect to charge q1 in a direction along a line joining these two particular charges. So let us consider that the magnitude of that particular force is indicated by symbol F2 with bar symbol indicating that it is a vector quantity. Now let us try to write a mathematical expression of this force in terms of vector domain. So we can write here as F2 bar, which is going to be equal to q1 multiplied by q2 whole divided by 4 pi epsilon naught multiplied by distance square. So here the distance between these two charges is indicated by symbol R12 bar. So here R12 bar magnitude square multiplied by the direction of this particular force. The direction of this particular force is defined by this unit vector. So here we need to multiply this expression by r cap. So from this equation it is very clear that the force experienced by charge q2 because of charge q1 is along the direction of this unit vector, or it is along a line joining these two particular charges, and the magnitude of that particular force is represented by this particular equation, that is q1 into q2 divided by 4 pi epsilon naught multiplied by r12 square. Let that equation number 2. Now let us try to understand the concept of electric field intensity. What is electric field intensity? So for that, let us consider an experiment in which we have placed our charge q1 at the center of a sphere, and let us consider that the radius of that particular sphere is indicated by symbol r, and on the periphery of that particular sphere we are going to place our test charge indicated by symbol qt. So what we have done, at the center of that particular sphere we have placed one charge which is indicated by symbol q1, another charge which is our test charge, it is placed on the periphery of that particular sphere, and the radius of that particular sphere is indicated by symbol r. Now with respect to our previous discussion, it is very clear that this charge q2 will experience a force with respect to charge q1, maybe in attraction form or maybe in say repulsion form. So let us consider that both the charges are of same polarity. So definitely charge q2 will experience a force with respect to charge q1 in repulsion form. So this arrow will indicate the force experienced by charge qt. Now from the previous discussion it is very clear that if you move the position of this test positive charge anywhere on the surface of this particular sphere, suppose if you placed the test positive charge qt at this particular location, then at this location also this charge will experience a force ft along the radius of that particular sphere in this particular fashion. In the same way, if you change the position of test positive charge and if you placed that particular positive charge over here, then in that case also this charge will experience a force along a radius in outward direction like this. That means from this particular experiment it is very clear that if you place this particular charge anywhere on the surface of that particular sphere, this charge will always experience a force of repulsion. That means there exists a vector field because of which this charge will try to move away with respect to charge q1. That vector field is known as electric field intensity. So what is electric field intensity? From this particular experiment, electric field intensity is nothing but a vector field because of which this charge will experience a force with respect to charge q1. That vector field is called as electric field intensity, and it will exhibit everywhere with respect to charge q1. Now let us try to write a mathematical expression to calculate the value of force experienced by charge qt. So mathematically we can write ft bar, which is nothing but q1 into qt whole divided by 4 pi epsilon naught multiplied by r bar square multiplied by a unit vector along a line joining these two charges. So let us consider that the unit vector is indicated by symbol capital R cap. So here we need to multiply it by capital R cap. And if you are interested to write in scalar form, the equation can be rewritten as ft is equals to q1 into qt whole divided by 4 pi epsilon naught multiplied by r square. Let that equation number 3, where r indicate the radius of that particular sphere. Now mathematically this electric field intensity indicated by symbol capital E is defined as force per unit charge. Force per unit charge. So in this case, if you are interested to calculate what will be the intensity of electric field experienced by this test charge with respect to charge q1, then in that case what we need to do, we need to write the expression of force from equation number 3, and charge is replaced by our test positive charge, which is nothing but qt. So we can write here as q1 into qt whole divided by 4 pi epsilon naught into r square. So this is the expression for force which we got from equation number 3 multiplied by charge. So here our test positive charge is qt, so here we need to write qt. So this qt will get cancelled out, and finally we get the expression to calculate electric field intensity as q1 divided by 4 pi epsilon naught into r square. This is a mathematical expression to calculate the value of electric field intensity experienced by this particular charge with respect to charge 1. In the same way, let this equation number 4, we can also write this expression in vector form. So in vector it is going to be like this: E bar equals to q1 divided by 4 pi epsilon naught, here r bar magnitude square multiplied by a unit vector along a line joining these two particular charges. So in this case our unit vector is capital R cap. So here we need to multiply this particular expression by capital R cap. So this expression will indicate the magnitude of electric field intensity, and this particular factor indicate the direction of that particular electrical field intensity. So it is a vector field, because of which this test charge is going to experiences a force of repulsion with respect to charge q1, and that vector field is known as electric field intensity. Now let us try to calculate what will be the unit for electric field intensity. So from this definition we define electric field intensity is nothing but force per unit charge. So the unit of electric field intensity is Newton per Coulomb. Why it is Newton per Coulomb? Because force unit is Newton and charge unit is Coulomb. So the unit of electric field intensity is Newton per Coulomb, and in some cases we also specify this electric field intensity as volt per meter. So basically we are having two different unit to represent electric field intensity. Either we can represent in terms of force per unit charge, which is nothing but Newton per Coulomb, or we can represent it by taking this particular equation as volt per meter. Now let us try to discuss the concept of electric flux density. What is electric flux density? Electric flux density is indicated by symbol D, and mathematically it is defined as how many number of flux line coming out from a unit area. So electric flux density is nothing but flux per unit area. Now Professor Michael Faraday experimentally found that the electric flux indicated by symbol psi is proportional to charge, and the constant of proportionality for SI standard unit is going to be 1. Therefore, we can write psi is equals to Q. So, by using these two particular equation, we can write electric flux density is nothing but charge per unit area. Now, with respect to our previous case, that means we are having a sphere of radius r. At the center of that sphere we have placed a unit charge q1, and somewhere over here we have placed a test positive charge q2, and because of that vector field, this charge q2 will experience a force of repulsion in this particular direction, that is ft bar. Now let us try to calculate what will be the number of fluxes which are coming out from this particular sphere through a unit area, and that is nothing but what? Electric flux density. So here mathematically we can write D is equals to this QT whole divided by area. Now area is nothing but the area of sphere, which is going to be 4 pi r square. Let that equation number 5. But from equation number 4, we know that electric field intensity is nothing but charge, it may be a test positive charge or it may be a unit charge, is nothing but 4 pi epsilon naught multiplied by r square. Now if you compare these two equations, mathematically we can write this electric field intensity is nothing but D divided by epsilon naught, or we can write D equals to epsilon naught multiplied by E. So this is a relationship between electric flux density and electric field intensity of a given electric field. You may write this particular expression in vector form like D bar equals to epsilon naught multiplied by E bar. Remember one thing, this E naught indicate the permittivity of free space. That means these two equations are strictly for free space, or you can say vacuum. Suppose if you are interested to write a relationship between electric flux density and electric field intensity for any other medium, in that particular case what we need to do, we need to replace this E naught by E, or you can say eta. So for any medium apart from free space, we can write the relationship between electric flux density and electric field intensity as D equals to epsilon multiplied by E, where epsilon indicate the permittivity of that particular medium, which is nothing but a product of epsilon naught and epsilon r, where epsilon r indicate the relative permittivity of that particular medium. So this equation we need to apply for any medium other than free space. And if you are interested to study the conduction and breakdown of electric field in vacuum, in that particular case we need to apply this particular relationship. So ultimately the relationship between electric flux density and electric field intensity is governed by this particular equation. And what will be the unit for electric flux density? So the unit of electric flux density from this particular equation we can write as charge coulomb area meter square. So the unit of electric flux density is coulomb per meter square, which is very, very important. Now let us try to discuss the concept of Maxwell equations. Maxwell's equation. Maxwell equation plays an important role in order to study the behavior of electric field, in order to study the behavior of magnetic field. And there are basically 4 equations which was written by Professor Maxwell in point form. It is given by, first equation is del dot D bar is going to be equal to rho v. Second equation is del dot B bar is going to be 0. Third equation is del cross E bar, which is going to be equals to minus dou B bar by dou T. And fourth equation is del cross H bar is going to be J plus dou D bar by dou T. These are the 4 Maxwell equation in point form. Now let us try to understand the physical significance of these equations one by one. So the first equation is del dot d bar equals to rho v. Here rho v indicate volume charge density, charge per unit volume, that is volume charge density. And if you see this particular mathematical expression here, in first lecture I told you that del is nothing but an operator. Basically it is a vector space function, and d indicate electric flux density. It is again another vector, and here we are taking dot product of del with respect to a vector. So basically this operation is called as divergence. Very good. This operation is called as divergence. So divergence is nothing but what? When we take dot product of a del operator with respect to another vector, and if you are interested to study how this vector field is going to vary with respect to space in given 3-dimensional space, then that particular objective is called as divergence. So Maxwell equation 1 indicate that if you take the divergence of any electric field, then in that case the output is going to be a volume charge density. That means it is possible for us to separate positive charge and negative charge with respect to each other. That means if you are having a sphere and if you are interested to provide a positive charge on its surface, so with the help of this particular equation we are capable enough to provide a positive charge, or we are capable enough to maintain a net positive charge on its surface. And if you enclose this particular sphere in another what we can say sphere, then there will be a net electric flux coming out from this particular sphere. So this is the significance of Maxwell equation 1. That means if you take the divergence of electric flux density, it is going to be equal to a volume charge density. And if this equation is going to be 0, that means the net electric flux coming out from this particular charge or sphere is going to be 0. Second equation is divergence of magnetic flux density. This B indicate magnetic flux density. So if you take divergence of magnetic flux density, it is always going to be 0. The physical significance of this equation is that we are not in a position to separate North Pole and South Pole from each other. What is the meaning of this? Suppose if you are having a bar magnet and we know that it has 2 poles, this one is say North Pole and this one is going to be South Pole. Suppose if you cut this particular magnet into 2 sections, what will happen? We are having 2 sections like this. Now this point is north, this point is going to be south, this point is going to be north, and this point is going to be south. Suppose if you further cut this particular section into smaller one, so here we are having a structure like this. So each piece has 2 poles, north, south, north, south, north, south, and north, south. That means it is not possible for anyone to separate North Pole and South Pole with respect to each other. That is the physical significance of this particular equation. That means the net magnetic flux coming out from a sphere is going to be 0. Why it is going to be 0? Because if you consider a sphere, in that particular case we are having both North Pole as well as South Pole available inside it. So the field will start from North Pole and it will end at the South Pole. So the net flux coming out from that particular sphere is going to be 0. So that is the physical significance of Maxwell's second equation. That means if you take the divergence of magnetic flux density, it is going to be always 0. But here it may be 0 or it may not be 0. If it is 0, that means the net electric field coming out from that particular surface is going to be 0. But we can have the flexibility to decide whether we want that particular situation or we not. But in case of magnetic field, if you take the divergence of magnetic flux density, it is always going to be 0. That means it is not possible to separate North Pole and South Pole with respect to each other. Third Maxwell equation indicate that if you vary magnetic field with respect to time, then it is responsible for the creation of electric field in space. Or we can say that space varying electric field is responsible for the production of time varying magnetic field, and this negative sign indicate the significance of Lenz's law. That means it will oppose its root cause. So ultimately it is nothing but a combination of Faraday law and Lenz's equation. So Maxwell equation 3 indicate that space varying electric field is responsible for the production of time varying magnetic field. And if you see this particular operation carefully, it is nothing but curl. Why it is curl? Because here we are taking a cross product between our del operator and another vector field. So basically it is nothing but curl, and with the help of this curl we are trying to identify how the electric field is going to rotate with respect to given space. And when we make that particular arrangement in which we are capable to create the space variation of electric field in a given space, then it is responsible for the creation of time varying magnetic field. That means electric field से हम लोग magnetic field जो है वो generate कर सकते हैं. That is the significance of equation number 3. And equation number 4 indicate that space varying magnetic field, here H indicate magnetic field intensity. Just like we are having electric field intensity in electrical domain, in the same way we are having magnetic field intensity in magnetic domain. So if we take the curl of magnetic field intensity, that means if we vary magnetic field with respect to space, then in that case the output we are getting as electric field which is time varying in nature. Or we can say that a space varying magnetic field is responsible for the production of time varying electric field. And here we are having one more operator which is called as J. This J is called as current density. So these are the 4 Maxwell equations based on which we are in a position to understand the behavior of electric field and the behavior of magnetic field, out of which equation number 3 and equation number 4 tells that electric field and the magnetic field are analogous of each other. That means if you vary electric field in space, we will get time varying magnetic field, and if you vary magnetic field in space, we will get time varying electric field, which is very, very important. Thank you.